So this is the beginning of worksheet 6 where we're looking at comparing proportions. This pulls from, or at least this first section pulls from chapters 8 and 9, which is a little bit of review from your previous stat class. On worksheets 2 through 4, so that is when we were looking at simple and multiple regression and 1 and 2-way ANOVA and 2 sample t-tests, every study in the class, all of those topics, and the 2 projects that we have dealt with have used a quantitative response. But now we're going to ask the question, what if the response is categorical? So remember, all of the conditions that we've looked at for every test that we've done, every hypothesis test, every confidence interval we've done, we've always specified the nature of our variables, both the response and the explanatory variables. And up until now, the response has always been one quantitative response, and the explanatory variables may be quantitative or categorical. But now we're changing the response to be categorical. So we can identify the kind of inference, or excuse me, the kind of test that we're doing based on the kinds of variables we're using. And we've talked about this a little bit throughout the semester, but this is going to become really important now because we are changing the type of the response variable we have from quantitative to categorical, and that means we're going to be dealing with a different parameter of interest, and that means we're also going to be dealing with different tests to investigate that parameter. So let's start off with an example to help us understand this. In this example, we have, we're going to be looking at whether babies prefer helpers versus hinderers. So this is a study that's reported in Nature magazine, or the Nature Journal. And in this study, researchers investigated whether infants consider an individual's actions towards others in evaluating that individual as appealing. In one component of the study, 10-month-old infants were shown a climber character that could not make it up a hill in 2 tries. Then the infants were shown 2 scenarios for the climber's next try. One where the climber was pushed to the top of the hill by a helper character, and one where the climber was pushed back down the hill by a hinderer character. After viewing these scenarios several times, the infants were presented with the 2 characters from the video. 14 of the 16 infants chose the helper over the hinderer. That is, 14 of the 16 infants preferred the helper to the hinderer. We are given now a sample proportion, a p hat of 14 over 16, or 0.875. So in our sample of 16 infants, 14 of the 16 preferred the helper. Now, what the real question is back to here. We want to know, do infants consider an individual's actions towards evaluating others? That is, do infants prefer helpers to hinderers? Now there are only 2 options in this case. This is like flipping a coin that has a helper character on one side and a hinderer character on the other side. And we want to know, is this coin balanced more towards helpers, towards hinderers? So our null hypothesis is that babies choose faces, or that is the characters, randomly, without preference. And if that is true, if in the population the babies really have no preference and they're choosing from these 2 characters randomly, then that would mean that in our sample, babies chose the helpers more often just by chance. So that would mean that chance explains the difference, or this higher proportion. The alternative, however, is that babies really do have a preference, that babies do take into account individuals' actions towards others, that babies are perhaps empathetic. And in this case, then, our alternative is that babies genuinely prefer helpers to hinderers. Now, how can we translate these 2 statements these two plain language statements into statistical hypotheses about a parameter. Here we have a sample proportion. What would be the population parameter of interest? And furthermore, what would be the hypothesized values for the null and alternative hypothesis? So please pause this video and then pick back up when you think that you have an answer and check your work with mine. Yes, I hope that you identified that the population parameter of interest would be the true population proportion. In this class, we're going to call that pi. We're going to stick with the idea of pi, or Greek letters, being population parameters. This is consistent with what we saw for population means and population slopes. So a population mean was denoted mu, which was the Greek letter m. And we used beta and alpha in our regression equations, which were Greek letters representing the slopes and the intercepts of our regression model. In this case, we're going to use pi as our population proportion. So pi is the Greek letter p, and we're going to use that to represent a proportion or a probability. So in our null hypothesis, if babies choose faces just at random, and there are only two options, they can either choose a helper or a hinderer, then that would just mean that pi equals 0.5. There is a 50-50 chance that a baby's going to either look at the helper character or the hinder character in determining which one they're going to look at. That is, there really is no preference. The alternative hypothesis is that babies really do prefer helper characters to the hinderers. And in that case, that would mean for our statistical alternative that pi is greater than 0.5. In order to help this make sense, we really do need to define our parameter of interest. In this case, pi is the true proportion of infants who prefer the helper to the hinderer. Or we might think of this as pi as the true probability that a baby prefers a helper to a hinderer. But either way, if pi is a true proportion of infants who prefer helpers to hinderers, and if babies really do prefer helpers to hinderers, then that true proportion should be greater than 1/2. More than half of the infants in the population should pick the helper over the hinderer character. So our next question is then, how could we set up a simulation for this study? And I already kind of gave a hint to this earlier on when I said we have these two characters and we might think of this as two sides of the same coin. So how can I model? So when we set up a simulation, what we're really doing is saying, how can we model this just by chance, this alternative hypothesis using simulation? We've done simulation examples before. With a two-sample t-test, for example, we set up the scenario where there was no relationship between the distance a football gets kicked and the temperature by breaking the relationship and randomly dealing out the distances between two piles, a hot pile and a cold pile. We could do this in this case as well, only it's actually a little bit simpler. But when we set up a simulation, we're saying, how do we model the just by chance scenario? That is the null hypothesis. So what can we do? How can we set up, is there something in the real world that we could use that has a 50-50 outcome, where we can, take that and automatically use that and use that as a model for this scenario where babies are picking helpers or hinderers 50% of the time? There are a lot of options out there. See if you can identify one, pause the video, and then regroup with me. One of the possible options you might have identified was saying, well, let's use a deck of cards. Half of the cards in the deck are red, half of the cards in the deck are red, and half of the cards in the deck are black. So what we could do is we could just shuffle the deck cards in a regular 52 card deck really well and pick a card at random. And if that card comes up red, we'll say that that's a helper, and if the card comes up black, then we'll say that's a hinderer. And we could do this over and over and over again. So we'll pick a card, see that it's red, say it's a helper, put that back in the deck, shuffle the cards up well again, and then keep picking up cards like this over and over. Another possible way that's actually even more straightforward is to use a coin toss, and that's the one that we're going to use. So we'll use a coin toss. We're going to assume that coins really do have a 50-50 chance of heads or tails. So the coin toss is going to represent a baby's random choice under the null hypothesis. We had 16 babies or 16 infants in the sample, so that means that we need 16 coin tosses to simulate this particular sample. If we were using the cards, we would have to draw one card at random, look at its color, put it back in, shuffle up, draw another card, and do that 16 times. So we would have to draw 16 cards with replacement and good shuffling in between 16 times. We also have to identify what we're going to call heads and tails. In this case, let's just say heads is a helper, and that means tails is a hinderer. And because we are assuming that heads and tails are equally likely, that means that our outcomes, in this case, helper and hinderer, are equally likely. And that means we have identified this null hypothesis to be true. So if one coin toss represents one baby's random choice under that null hypothesis, then when we flip the coin, we are either going to get a helper or a hinderer with probability 0.5. Then we're going to record the sample results. And that means we're going to record the proportion of heads, which in this case is the hinderers, and we'll do this multiple times because that would just give us one simulated sample. We need to repeat this maybe 1,000 times to get a good sense for how often we would see a sample proportion like the one we have, where we had 14 out of 16 helpers preferred. So this will get us a sense of the distribution of that p-hat when the null hypothesis is true. If we look at the notes, we'll see this is an example of that distribution. We have here our results, our p-hat of 0.875 or 14 out of 16 for our current sample. This distribution here, this is the distribution of all the possible p-hats when we do this 1,000 times. So this is 1,000 p-hats for 16 coin tosses at a time. What we observed was a p-hat of 0.875. All of these bars represent all the other possible p-hats that we might have occurred and did occur if we were to repeat this simulation 1,000 times. So these bars are many, many, many possible p-hats. We can see some of the p-hats, most of the p-hats are around 0.5, which is what we would expect. But then we also see that sometimes, even with a fair coin, we can get a p-hat of pretty close to 1 or a p-hat of pretty close to 0, which means that we could get 16 out of 16 heads, or we might get no heads out of 16, but those are much less frequent. So, given this simulation distribution, does it look like our sample p-hat of 0.875 is a likely occurrence if there really is an equal distribution, or excuse me, an equal probability of outcomes between picking a helper and a hinderer? That is, if babies really are just choosing between these two characters by chance. Pause this video and see what you think. In this case, no. Most of the time, we're going to expect to see p-hats when we flip the coin 16 times, around 0.3 up to maybe 0.6-ish. And we observed a p-hat of 0.875, which is really far away. It's a really unusual observation if babies really are just choosing by chance. So, the p-hat we observed is very unusual if the true probability is 0.5. So if on average we're going to expect to see a p-hat of around 0.5 in the long run, getting a p-hat of 0.875 is really extreme. In fact, the p-value for our right-tailed test based on this simulation is 0.0032. That is, we observe something like this or bigger. We're going to see a sample proportion like this or larger only about 0.3% of the time. This is very strong evidence against the null hypothesis. And in support of the alternative that babies prefer helpers. So we just identified a question with a categorical response, the response being type of character. The levels of that categorical response are helper or hinderer. We identified how we might set up a simulation study to model the null hypothesis. I gave you the results of one possible run of that simulation with 1,000 repetitions. And we found that we have very strong evidence that if that null hypothesis, that babies are choosing between the levels of that categorical response just by chance, this is a very unlikely outcome to occur. So we have very strong evidence against that null hypothesis and in favor of the alternative that babies prefer helpers. In the next video, we're going to look at how do we move away from a simulation study and into a theoretical distribution, which would be the z-test and z-confidence intervals for one proportion.